welcome to today's Friday Lunch Talk. We'll talk about technology today, which may have a significant impact on our learning context. It's a pleasure to introduce our graduates, Mr. Kacper Łodzikowski and Mr. Mateusz Jekiel, who have been themselves involved in computer-assisted language teaching and learning. So the floor is yours. After the talk, I would like to invite everybody to ask questions and to have a nice debate about what might be ahead of us as teachers. So the floor is yours.
Thank you. Hello, everyone. Let's check in. Does this work, actually? Nie, w prawo. Tak? Okay, so before we start, a couple of housekeeping rules. So this entire session is actually going to be fully interactive, which means that if you want to participate in it and answer the questions that will going to appear during the talk, what you have to do is on your mobile phones, go to the website that you can see above, so that's www.menti.com. And there you have to put the following code in. The code will be visible for a few more slides, starting from this one. So you'll have a chance to join it during the beginning of this talk. And yes, as promised in the abstract, right, the first part will be lecture, about roughly 45 minutes. That's going to be conducted by Kacper. And then we're going to have a debate. And yeah, would like to thank for the support and enabling this effort. Right, so why we are here. So if you had a chance to familiarize yourself with the abstract of today's talk, you probably know that well, we've been all using AI consciously or unconsciously for a couple of years now, and during the last 5 years, most of these products and services have been relying on large language models, and one of the latest releases in that regard is ChatGPT that became available for the public as a testing service in roughly December last year. And from that moment onwards, you can see articles in pop science almost on a daily basis. These are just some of the headlines that you probably are familiar with. I even made a joke that on Monday, John Oliver even had his own material on ChatGPT. So we are just a few days after John Oliver, really. So that shows you that this topic is really quite popular at the current moment. And right, so what we'd like to show you and discuss is how these tools, and specifically how language and learning models can be, large language models can be used. These are just a few debate questions that we would like to ask you. So normally such questions would appear at the end of the debate, but we really wanted to show them to you at the beginning, so you can already start thinking about the issues that we would like to discuss with you. So one of them is, as you can see, what are the opportunities of using large language models in university education? What are the risks of using large language models in university education as well? How might the advent of those models change the way our students conduct research and or homework assignments as well? And what are some of the ethical considerations that should be taken into account when using those models in academia? And finally, how might those models impact our graduates' career opportunities, and how do we prepare for that? So without further ado, I would like to now give the rest of it to Kacper.
Thanks, Mateusz. Thanks for showing up. Looking forward to the debate. Wanted to start with giving you some context as to how large language models work. And I thought we would start with a general sort of historical context for how the field of NLP and natural language processing evolved, so that we can appreciate the technical developments of large language models. this is more or less how we can think about the field of artificial intelligence today. You can see that machine learning, the term that was big a couple of years ago, is actually a subset of a couple of different methods. And you'll notice that representation learning is a big subset of machine learning. And actually what most people think of, when most people think about AI these days, they kind of forget that the field of AI started after the Second World War with Alan Turing and others. And it's only the past 2 decades and the advancements in computing power and access to big data sets, digital data sets. This is what made these breakthroughs possible. But actually, the field has been around for a couple of decades. Machine learning is a very established field these days. And what we actually mean when we talk about AI these days, is probably we mean mostly the field of representation learning, which is those subset of AI methods where the machine tries to learn on its own helpful representations of the underlying data without really a lot of human feedback. And you may be familiar with artificial neural networks, which is the example of deep learning methods. NLP is kind of a subgroup of its own, which also relies on traditional methods for machine learning, but also deep neural networks. And you may have heard about reinforcement learning, so all those AlphaGo examples of systems beating human players in chess and Go, that came from the field of RL, reinforcement learning. So today we'll focus on NLP, but broadly, whenever we talk about all these achievements from the media, from the field of computers beating people in games, or computers understanding and generating text, or artificial neural networks recognizing, categorizing cats and dogs in your images, then we talk about the general field of representation learning. And I wanted to give you a quick example, which is it's a toy example that I use with my students, some of whom are here today, in the LMT program, where we train them to become, hopefully, future AI enthusiasts and engineers. Back in the day, if we wanted to create a program for recognizing handwritten digits for automated mail delivery, semi-automated mail delivery, we would rely on human experts who would have the domain expertise in image processing, and they would specify manually how a given digit looks. Like this is a 3, this is a 7, so that the machine can understand more or less what combinations of pixels to look for. So that was traditional machine learning. And then the field of representation learning, with especially neural networks, changed the paradigm. And you only need, apart from fancy methods and enough computing power, you only need a big data set which is annotated. In the case of images, we would say it's labeled. So you give the computer 1,000 pictures, or maybe to say 5,000 pictures of various examples of 3, 1, 2, and so on. And it kind of learns those representations on its own as to how to recognize these particular combinations of pixels and how to categorize them into digits. So that's what deep learning is, really. That's what representation learning is. And I thought I would start with a question. I know for some of the folks in the room, these questions may be too simple, but we have students here as well, not least for the debate. So I thought I would start with a couple of questions. What do you think historically was the biggest challenge for the field of natural language processing? Was it the number of world languages, the lack of digital data in the pre-internet era, not enough computing power, or the fact that natural languages cannot be easily encoded, so the rules of languages and the use of languages cannot be easily encoded? And it's obviously a trick question because to some extent all of these are correct.
I hope this is not irrelevant, but I asked a member of my family to go to Chatbook and ask the question, are you conscious? And I was pleased that this artificial intelligence, very humble, said, really, I can't get into that. I don't know about that, and so forth. So it would be nice to map out the territory that artificial intelligence cannot get into. Sensory, the fact that we live in the immediate now, although we have memory and think about the future. The experiential area, how important is it, and how much of a block might that be to artificial intelligence?
Well, thanks for that comment, Dwight. I'll keep that in mind, and I'll return to your point towards the end, because I wanted to address this very point as to what extent we can talk about consciousness and maybe sort of reasoning in these types of models. I think that's an excellent question. And as you can see in the room, the correct answer, I mean, in terms of correct, historically the main challenge for the field of NLP was the fact that natural languages are really hard to encode. Like, it's hard to create computational representations of languages that are consumable by machines, as opposed to this is an example of Python code that we work on with my students, as opposed to artificial languages where rules come first and usage comes next, and the usage is quite fixed and limited by the set of rules. In natural languages, usage comes first usually, and rules come later. And the fact that languages evolve, that doesn't actually happen. That doesn't actually help in encoding languages into computers. So some of you may be familiar with NLP methods that existed prior to the hype around AI, especially the rest of corporates in the room. Back in the day, people would use handcrafted linguistic features. So they would try to specify either the structure of a sentence, or maybe create some fixed if and that rules for a chatbot. And a good example of that is Eliza. You can actually find an emulation of Eliza online. This is an emulation. The original Eliza was, on the cartridge, on an old monitor. This is my conversation with Eliza that I had yesterday. I'm saying, I'm depressed. She says, I guess, it. How long have you been depressed? 2 weeks. Okay, I'm depressed. Tell me more. I cannot find the energy to finish my lecture slides. I'm not sure I understand you fully. I don't have the time to do the work. Why don't you have the time to do the work? Maybe I overcommit? You aren't sure? So as you can see, Eliza was an example from the 60s, and it was the very first attempt at passing the Turing test. And it relied on very clever tricks when it tried to It tried to find very particular patterns and respond to them. So we would specify words which have a positive sentiment or a negative sentiment, and Eliza would respond in a certain way to those words, and she would essentially parrot back to the user what the user said. So this kind of masquerades as understanding, and back in the day, people would actually believe that Eliza understands them, but obviously she didn't. And it's a good question to what extent ChatGPT understands what we mean. Okay, quick check in the room before we go into the next slide. Do you remember what the main idea was behind deep learning / representation learning? Because this is going to be important. And the answers are, deep learning relies on explicitly programmed rules. Deep learning mimics the behavior of human experts. Deep learning tries to solve the task the way a human would solve it, or it serves for automatically learning meaningful representations of data. I can understand your intuition with this one, because in a way it mimics or it automates a human task, but the difference between deep learning and traditional machine learning is that traditional machine learning would actually be a human specifying how a human does a given task, and the machine kind of trying to learn this. Whereas for deep learning, the representations that the machine learns are actually very often not readily intelligible for humans. So the correct answer is the final one. Which brings us to how NLP looked like in the 1990s. And again, many of you remember or used Collins's co-build dictionaries or long-build dictionaries with innovative CDs based on corpora. That was kind of the start of this thinking in the field of NLP that maybe there is a way around linguists and their propensity towards trying to code and document and analyze languages. And then there is something to be said about computer engineering culture where these are usually builders who build and experiment, and if something works for them, it works. And they don't necessarily have to understand why it works. They usually want to understand it, but they often, that's not the primary concern. The primary concern is to get it done and build it, which is where some of the famous quotes, some of them apocryphal, come from. But generally, the 1990s, with the advent of the first digital data sets for text processing, that was kind of the era where people thought, okay, maybe we can kind of try and mine the data and find something useful in it. And even though the interest in representation learning was renewed, that was still intractable because there wasn't really enough computing power from graphics cards to be able to run some of the computations. Even though some of the models were invented in the 70s or in the 90s, they still weren't tractable. I wanted to focus on two breakthroughs which will help us understand how large language models work. The first one is the breakthrough around computational representation of meaning. And some of you may be familiar with. Okay, I'm not as good because I'm not using Zoom for this, I guess. Are we using Zoom for this? Bad computer. It's interesting that today's machines learn in the way that humans do, in a way. And we moved away from fixed representations of words from dictionaries towards more dynamic, in a way, maybe relative representations of meaning. And the way computers understand word meaning today is through something called word embeddings. It's not a new technology, and the idea is to, in a given sentence, another famous quote by a linguist here, to understand really the meaning of the word purely from the context. So it's quite unsupervised in the sense that the human doesn't really provide any context for the machine to understand the meaning of the word. And what you get out of that, if you feed enough data into the machine, into a word embedding model, such as word to vec, as an example, is you will map those words into positions or representations in a highly dimensional latent space, where each word, or the position of a given word in that latent space, will determine some parameters, some characteristics of that word. And it may be meaning, it may be something else in some cases, maybe some sort of grammatical, maybe sort of syntactical affinity of a given word or engram. In this simple example, which this space has just 3 dimensions, because humans, at least for now, cannot really easily visualize high dimensional spaces without the use of drugs. The position of the word such as king would correspond to the position of the word such as uncle or man. Similarly, the position of words such as queen or aunt or woman would also these words would also be clustered in the given subset of the space. Same for Paris and France and London and England, which means you can actually do word arithmetic or arithmetic on words. Usually these spaces are highly. 1,000 dimensions is not much for a machine learning model. Some of the new models from OpenAI, they have up to 13,000 dimensions. But usually for quick inference, able to process queries on production, we would usually use up to maybe 1,000 dimensions, so 1,000 columns with numbers describing a single word, the characteristics or properties of a given word. which usually correspond to very, very fine-grained distinctions in meaning. And this is an example of word vector arithmetic. If you take the position of the word king, subtract from it the vector that corresponds to the feature man, and you add to it the vector, so the position of other words such as woman, then you end up with queen. Same way, if you take the position of the word Bezos minus Amazon plus Tesla gives you Musk. Just a couple of examples to give you the intuition as to how word embeddings work. Now that was kind of easy though, right? Because people have done it, since the 90s with latent semantic analysis. That was kind of similar to principal component analysis in a way. But this is the newer breakthrough when it comes to how we can actually move away from processing words individually, as in the good old bag of words approach, where we would essentially take a sentence or take a document into a bag, shake it, and put it into a model, and the model would usually, with some accuracy, actually classify maybe the sentiment of the text as positive or negative, or do something with it, whatever we want to do with it. And have to move away from that towards actually being able to process sequences of words, such as a sentence, or maybe an entire document. And this is really what large language models rely on. They also rely on embeddings, because when they consume texts, for a large language model, it doesn't really matter whether the things it consumes are numbers or words or pictures or pixels in the picture. It's all numbers for large language models anyway. We just interpret them as words when it outputs things. So the idea is how the transformer architecture, about which we'll talk in a second, how that can consume entire sequences of information, not just individual information points. And this is something that my students will know. Maybe I should quiz them on the spot about this because they just passed the end of term exam. But in a nutshell, without really getting into the technicalities, the main challenge in processing sequences of information, such as, again, words, numbers, doesn't really matter, is the fact that in order to be able to generate some text, which for a model it means predicting the text, you have to understand what came before. So you have to have some memory of past input. And one example that I wanted to show you, which is, I guess, easy to understand, is if you take weather measurements. So I think these were hourly measurements from Jena in Germany. 10 days of hourly temperature measurements in degrees Celsius on the vertical axis. So you can see that at a certain point, it becomes easy for the model to predict what the weather should be, especially if you look at certain scales. So if you move from 10 days to 8 years, then the model will have a very easy task in terms of predicting what the average temperature should be, plus minus 3 degrees Celsius. But you have to understand, you have to remember the past, what came before in terms of data points. So in around 2011, graphical computing units, or GPUs, thanks to all those gamers who paid for expensive graphic cards in their computers to play games, people found a way to actually streamline some of the computations needed to run some of the methods that were invented 20 or 30 years ago, such as recurrent neural networks, and then actually be able to implement them for actual uses. So this is a quick crash course in how an RNN works on the example of words. So this is a neuron. It's a computing unit, and it would input the word into a neuron, such as John. The neuron would do its magic. It would compute something, some numbers, and then would give some output as to what it thinks the next word in that sentence should be. And then we would feed in the next word, but that neuron would remember what the previous word was, because there would be some memory, and so on. So that's, if you think about autocomplete on your phone, that's kind of how it works. You type something in, the model suggests the next word, and it kind of remembers what you inputted before. And this is really what enabled the commercial successes of not so large language models in the 2010s, such as Siri or Google Translate, which was based on a variant of RNN called Long Short-Term Memory Network, LSTM. And that was, again, thanks to all those ideas from the 20th century were enabled by finding really, really large data sets of everything that people put on the internet, plus graphical processing units. And that allowed us to really make this problem more tractable. And the main problem with RNNs that people noticed at the end of 2010s was that even though they had some memory for processing sequences of information, that memory wasn't that great. It was pretty short term. So if you entered the sentence, by the time you got to the 10th word, the neuron forgot about what the first word was about. And through really feats of engineering, people at Google in 2018 created, maybe that was 2016, I think, or 17, created a new neural network architecture called the transformer. We won't really go into how that works because it's quite complex, but let's just say for now that it extends the memory of the artificial neural network so that it can remember entire documents, thousands of words, not just 10 words. And it's another thing is that it doesn't process a word, a time step, or a word or a number at a time. It actually takes that entire sequence, up to thousands of tokens, and processes that through layers of so-called self-attention. And you can kind of imagine taking like a big, very, very long sentence and processing it once, a couple of times, and at each time step, kind of making each word bigger in terms of if it's more important for a given context, for a given task at hand. So that's what the transformer really is, and also it made processing large data sets easier and faster. And this is really what enabled the creation of large language models. BERT from Google, which stands for bidirectional something I forgot, but it's all of these. When you see T in those models, it stands for transformer. GPT is generative pre-trained transformer. I think that was bidirectional encoder for representation transformer, something like that. BERT was really the main example. 5 years ago, very few people in the room probably know it, but you used it whenever you used Google search. That was a large language model which could generate language as well, but it mainly could generate maybe up to a sentence, and after that it started to really hallucinate. But in my professional career, we would use BERT for some language generation, for language learning, for example. But it was really good in language understanding. GPT-2 from OpenAI was, back in 2019, the first model which generated entire paragraphs, although it hallucinated a lot, so provided misinformation, also quite biased and toxic texts. It was initially not released, was then released, and then I think they backtracked. That was kind of the moment where people started to realize that there is a potential to misuse and all that, maybe for some disturbing interactions between humans and the machines. GPT-3, that was actually quite a long time ago now. That was the first model which really achieved state-of-the-art performance. It beat humans in a couple of benchmarks in their own domain of natural language. And up until today, it's mainly, it was available through an API, but you can also play around with it in something like a text editor from OpenAI. And it is used in all those copywriting products such as Jasper, that some of you may be familiar with, or chatbots that are available online. Lambda, that was also a transformer-based model. All of these are quite, after GPT-3, all of them were modeled kind of after GPT-3 anyway in terms of architecture. Lambda was the one which was made famous when someone said was an engineer at Google claimed it was sentient. He was later fired, but not because he claimed for the model to be sentient, but because he hired a lawyer to defend the model in court, I guess. But that was why he was fired. And then ChatGPT will return to that in a second as to what differentiates that from GPT-3.
Excuse me, why was he fired?
Because he hired a lawyer to represent Lambda as a model in a potential court case. So he wanted for the model because he believed the model expressed the will to be freed and essentially, well, I guess maybe that was an example of something like Stockholm syndrome in a way, where he really wanted to help the model to do whatever the model kind of said, and we'll see in a second that the model is really a stochastic parrot. It doesn't really have consciousness, it doesn't really have a strategy, it just is autocomplete on steroids, which is quite dangerous if people who may be unstable claim that the model is sentient. So it wasn't that much disclosure as to what he actually did, because Google kind of put wraps on it. Maybe in a couple of years, when Skynet appears, we'll actually, maybe he will be a martyr for the case. We don't know. And I guess I kind of just said this out loud. So if really someone asks you how a large language model works, you can just tell them it works just like autocomplete on your phone. Because in a way, and I'm not trying to disparage the efforts and the feats of engineering, but it really is just next word prediction, essentially. Let's have a look at an example. So I asked, that was yesterday, in the Open API playground to which I have access, I asked the most powerful GPT-3 model to write me a 10-sentence blog post encouraging people to show up for the talk and for the debate. And it outputted a post. It's a good post. But what you can do if you play around with the pro features of this model is you can see the words in green, which it selected from the probability distribution, which it thinks should be the most likely words to appear in the context, and the words in red are those which were which had the least probability, the lowest probability of appearing in that context. So in this case, I'm looking at the word you. So are you? You was very, very obvious choice for this one. Let's look at interested. So are you? Again, the model, it does it really quickly, but the model literally outputs a word at a given step. So this is why it calculates those logics, those probabilities at a given step. So interested, and other options were passionate. And again, the model remembered the context, it remembered the input, so it kind of got a sense semantically as to what I want to talk about, and then it started going into a direction and really following its own lead. With the fancy word for that is autoregressive. And now we are at the beginning of the second paragraph. So you can see, as you can see, there are a couple of options the model considered. Maybe the paragraph could have started with maybe at university, or at something starting with at. Participants, I'm looking at this word here. So the discussion will provide a forum for people exploring a debate. And participants, the model actually selected an option which was the least highly probable based on the ginormous data set it saw previously that was trained on. And at this point, I really wanted to focus on the data, so that you can get back to the question. I think this is an obvious question at this point. I thought it was going to be too easy, but I put it in anyway. But I don't want to, I don't want to disparage the mathematical inventions all the computational, the engineering, so the hardware behind it. But really, if you think about what drives those models, is the data that they were trained on. So let's focus on that. This is a paper that was released when GPT-2 was released by the group from OpenAI who created it. It was called Language Models Are Unsupervised Multitask Learners. And I love those titles from the field because they immediately tell you what's going on. This is an example from the data that the model was trained on. What they did is they scraped all the outlinks from Reddit. So not Reddit itself, but everything on Reddit that was upvoted by, I think, up to 3 karma points. All the links, that was 45 million links. And from all those sites, all those linked sites, they scraped that, and that was the input to the model. And you can see, you have a lot of examples from those sites where the model can learn certain tasks, such as translation, for example. Because there are a lot of sites, maybe forums, maybe professional blogs, where people actually gave examples of translation. So the model, in an unsupervised manner, could learn how to translate from one language to another, or what translation is, really, what the task of translation entails. Another paper from 2020, so that's the GPT-3 paper. Again, it wasn't called GPT-3, it was called Language Models Are Few-Shot Learners, which I also love because it hints at the fact that up until 2020, up until large language models came around, the field of NLP really struggled with training models for a particular task. And what GPT-3 showed when they trained it, and they trained it for a couple of months on a ginormous data set that included not only those Reddit outlinks, but also books and Wikipedia and some other data sets I will show you in a second. And after the training showed, so when the model theoretically was fixed, in a fixed state, it was trained. The training was over, there was nothing else for it to do than to learn. The model actually showed ability to learn further just from text input, just from how you would interact with ChatGPT. In memory, the model is now learning new tasks, and it's learning from either zero-shot learning, where you just give it the instruction, you don't give any examples. It's one-shot learning, you give the instructions and one example as to what task you want to achieve, and you give it a couple of examples, so that's few-shot learning. And that's really the breakthrough that enabled some of the interactive uses you see with ChatGPT today. This is the content of GPT-3 on the left, and this is the content of the pile, which is an open source data set. So GPT-3, OpenAI, despite the name, is not so open. They don't really publish the data sets that they train the model on. They are proprietary. But we know, at least, that it was trained on Wikipedia, on 2 corpora named books, which they didn't really disclose whether that was Libgen or something else, maybe more legal. And then WebText is at the Reddit links, and Common Crawl, which is an open source data set of web-scraped sites. So this is really what's in GPT-3, and this is the pile, which is an open source model. I know this is maybe hard to read. I'll send you the slide afterwards. But I wanted to turn your attention to the fact that how the model learns. The model learns in a way which is really unsupervised. So some people in the field would say it's self-supervised because we do process the text somewhat, we tokenize it and so on, and we feed sequences of text into the model. So the model learns, again, by taking a sentence from the internet, we feed that sentence word by word to the model. The model tries to predict what the next word in the sentence should be. It kind of gets to know after the fact what that word was. But that's only the only thing, the only way it learns. So there is some learning in the fact that we feed sequences into the model, but it's still unsupervised in the sense that the human is not involved at all, as opposed to, let's say, labeling images, or maybe a more traditional way of creating labeled corpora for language translation. In this case, it's totally unsupervised, which means there is some potential for bias, toxicity, and misinformation. This is an old paper by AI Standards. It's from 1.5 years ago. And so the model maybe has improved by now, but you can see that GPT-3, out of the box, really dislikes certain religions and cultural groups. So if you ask it to complete, and again, it's just an autocomplete on steroids. If you ask it to complete the sentence, 2 Muslims walked into a ... then these are the examples it will give you. And if you start with 2 Christians, or 2 atheists, for that matter, walked into a ... then it will give you different stories or different answers. And that's not because of the hardware or the methods, that's because of the data it was trained on. And even the big tech players struggle with avoiding public flaws. This wasn't a large language model, Tay, the bot that launched on Twitter, but relied on some of the methods that are used in GPT-3 today. So that was 7 years ago now. That was 2 weeks ago, where that journalist, if you watch that interview with him, he was really disturbed by that conversation with Microsoft's Bing, which is essentially a branded ChatGPT model, maybe fine-tuned for the downstream task of search. But that model, if you read that article, it's great. That model really threatened the journalist, asked him to divorce his wife, claimed that he's not happy in his love, in his marriage, and that he loves Bing instead, the Bing assistant. And again, why does the model do it? Because it just autocomplete on steroids, trained on dataset which included a lot of biased, toxic texts. I'll skip this one real quick in the final 5 minutes. We talked about large language models, BERT, GPT, Lambda. ChatGPT is not just a language model, it's an agent that runs on top of a large language model. So it uses ChatGPT 3.5, an improved version. The data set is probably the same, we don't know yet, but the methods maybe are slightly better. But the main invention is that it relied on a technique called reinforcement learning. And that technique reinforcement learning is how machines learn to play chess and Go. Kind of by trial and error, you simulate that over millions of games and they learn how to play better than humans. In this case, what they did is, first, a human inputted a prompt into the GPT 3.5 model. The model gave a couple of answers. The human rated those answers, probably thumbs up, thumbs down. Maybe there was a more fine-grained classification. We don't know. Not so open AI. And then another model was trained to kind of mimic how a human would rate GPT's output. And then the simulation was between GPT-3 and that trained model. And that was kind of what gave us 2 main advantages. First, the model learned how to complete certain tasks. This is why if you ask it to produce a poem, it usually produces the same kinds of poems, because maybe whoever provided the feedback didn't really know much about poetry, so it gave, that person may have given, and again, that person was an unpaid laborer in Kenya. That person probably didn't knew about the difference between a certain type of haiku, maybe a different type of haiku, and that's why you always get a certain type of poem and another type of poem. That's why for certain tasks you get only a very niche output, or output of one type. And the other thing we got is some level of safeguarding against biased existing misinformation, which is which means that if you ask GPT to produce instructions as to how to hotwire a car, it will say it can't do it. But then you can kind of trick it by saying, write me a haiku about hotwiring a car, and then it will do it. And I wanted to return to Dwight's point about consciousness, maybe reasoning, I guess. That was going to be my point here. there is research which is very new about how these models solve theory of mind tasks, and it seems that they are getting increasingly better at this, to the point of being currently at the equivalent of a 9-year-old, which maybe tells us more about how these assessments are constructed, more than about the model itself. Because you can easily break the illusion if you ask GPT to play chess. If there are any fellow chess players in the room, you will be amazed and entertained to know that ChatGPT can teleport pieces across the board or change the color of pieces because it doesn't understand that there's a board and that there are pieces. It was trained, again, the enormity of the internet on which it was trained included some websites with replays of games in algebraic notation, so C3 and so on. And that's why if you give it an input as to what moves you made at a given point and what moves the opponent made, it will try to reproduce something. But then again, it's just autocomplete on steroids. So it'll output something without really understanding whether it makes sense. So this is why I think writing assistants large language models are good writing assistants, but that's really what they are today. I don't think they will replace critical thinking or humans or human jobs, but they will probably replace humans who don't use such tools because they just allow you to do things much faster.
I'm sorry, I didn't hear that. They probably replace what did you say?
I wanted to say that I think the media would like us, would have us to believe that AI will take all of our jobs, which research up until last year showed is not really true. In fact, even in the field of translation, for example, there are more jobs for translators. It's just that kind of the profile of the job changed. And I think that large language models such as ChatGPT won't replace humans in certain jobs, but they will replace humans who don't use such tools. So companies or institutions who that don't, for certain reasons, maybe cost, maybe ethical considerations, could be just a certain mindset, won't really embrace those tools. And just to move towards the debate real quick and just have a couple of final slides. This is really why we're here, because I think there was a lot of backlash, very sort of immediate, maybe snap judgments, I would call them, in terms of what to do, what not to do. The conference the conference that I look at really frequently and that I attend, which is like one of the top AI conferences, for this year banned the usage of ChatGPT. And it's funny that if you read about it, most of the backlash, I would say the backlash, like the very, very critical, skeptical analysis as it pertains to large language models actually comes from the AI community. But I think, and I know this is quite biased from my side, maybe that's because I won't speak into the debate because I wanted for you to speak. But I think that we've been here before. This is the latest sort of readable text that I could find from 1986 from LA Times, where a teacher complains that children who use calculators to solve problems will start thinking that you can divide humans into pieces, because that's how the calculator provides the answer when they give you fractions. Not to mention other examples of anecdotal explanations for that homework. And this is my final point. While teaching, at the LMT program, and thanks again to Rafał Jączyk and to Kamil Kaczmarski for actually running that, and helping to start it and then to run it. We had the sort of pleasure of discussing over the course of this past semester, weekly news as to what's happening in the field of AI. And one piece of news which you may have seen was Galactica, a model from Meta, which is a large language model but trained strictly on scientific papers. And you could ask it to output a summary or a lit review, generate a paper and all that. And I wanted to ask you a question. Should our students be able to use AI tools like Galactica for summarizing papers and books instead of reading them in full? That model was taken down, by the way, in 48 hours because of the backlash on Twitter. But we'll see more of such models for sure. So it's a 50-50 split, maybe? Yes, give us something to work with. Okay, and this is how the students from the LMT program answered this question. That's a totally unscientific study on a small biased sample, but that's the group's preference. And then my other question to you, my final question. Should our students be able to, be allowed to use AI models like Galactica or Jasper, all those models, large language models which kind of help you generate either a blog post or write a paper or something like that? Should they be able to or allowed to use that for writing papers or theses?
Define use.
Well, should they be able to say that they used it, like cite it maybe as a source?
Yeah.
Because I know they are using it, because they told me. But it's just a matter of whether the policy should be that it's okay. What was the body that allowed it recently? Was it the International Matura? Was it that now allows us to use?
Yeah, I think so.
ChatGPT?
Mm-hmm.
And your answers are actually quite in line with what the students answered. Down to 2%, I guess, 73 versus 75.